All right, let's just give everyone just a couple moments to kind of drop on in. We've got people just banging on the doors to observe another episode of Tech Art Talk Live. Give us an opportunity to really make sure that we've got all the pieces working. All right, good enough for now. Oh yeah, we've got good microphone. All right, let's get things rolling. Welcome, tech artists from around the world. It's Friday, and it is 12:30. It means it's time for another episode of Tech Art Talk Live. My name is Chris, and I am going to be your host for today's session. And for the last few weeks, well, actually for the last couple months, we've been working on HLSL programming, the shader programming, and the shader pipeline. And we're going to be finishing things up with this last kind of like mini series dealing with shadow mapping. And we're going to continue things on. Last week we went into the concept of projection mapping. This week we're going to be going on into the concept of depth mapping, which is also an essential property or an essential technique needed in order to get your shadows to actually work correctly. Now let's have a little review of what we're going on here. And so hold on a second. Let me get that on here. All right. Now, as we mentioned earlier before, last week we talked about projection mapping, and that is a way of projecting a shadow or projecting an image from a light onto the scene. And we use something called projection mapping in order to achieve that effect. And remember, what we had to do was we had to transform our texture map as being broadcast or being projected from the light itself, and we had to put it into NDC space. And the purpose of that is to make sure that it's no longer in the light specific space, but inside of the object space. So therefore, that's why we had to transform it into NDC space. Now this week, we're going to bring in another technique called depth mapping. Now, depth mapping is something kind of unrelated, but it is kind of essential because without depth mapping, we can't do the third and fourth steps, which is the projection with occlusion and then finally the shadow mapping. So what is depth mapping? Okay, now when we're projecting from a light, if we can see from this diagram here, if we're projecting from this nonagon here, and projecting it onto the scene, we see that it's projecting the shadow onto the thing, but parts of it are being occluded. Now, as you can see, what I just did there was I occluded part of the image. You can see that the teapot is actually obscuring part of the background, and because we don't want to see the shadow on the background of what's being occluded by objects in the foreground. And that is what the depth mapping is for, because that's an essential component in realizing that effect. And so knowing that certain objects are closer to the light than other objects, we're going to need to create something called a depth map in order to measure out all of the distances from the light to all the objects in the scene. And that's what is called a depth map. And so all the objects in the scene then need to be compared to their distance using the depth map as a way of judging relative distance from the object to the light that is projecting and creating the shadow. Okay, this is also rendered as a prepass. And what that means is that we're going to be using a render target again. If you remember render targets, we started talking about those a few weeks ago when we were dealing with post processes, and this is a lot of the same thing. Now, the render target isn't going to be screen size. We can control the size of our render target, and instead of screen size, it might be some kind of square image like 512 by 512 or 256 by 256. But needless to say, we're going to end up with a lot of these shadow depth images. And so therefore, we don't want to spend too much time and energy storing these texture map images. And they're going to have to be quick. They're going to have to be fast. And also, another magical thing about these these shadow depth images is that they're processed only inside of the vertex shader. Remember, in the entire graphics pipeline, the only essential step that any kind of object has to go through when it's rendered is going through the vertex shader. So therefore, this object needs to be done inside of the vertex shader. Okay, I have to make a disclaimer. I was not able to get this working effectively in the vertex shader, and so what I did was I kind of combobulated and reconfigured it to actually go through in a pixel shader component. And that's all done before, and I'll show you the considerations that I made. Okay, now remember, this render target is going to be off screen. That means we're going to render the scene, and it's going to be off sign, and therefore it's going to be pushed onto a quadrilateral. And so therefore what we have to do is we have to create some kind of post-process shader that's a little bit different than the post-processing shaders we were using before for visual effects. But what we're going to be doing is creating a post-process shader for measuring depth. And so what's a depth map? Okay, if you take a look at something like this, where we have this guy popping on the screen, notice that his hand is going to be whitest or brightest, or that's going to be the most it's going to be the brightest object into the scene. And as you go back into distance, the further we go back into the distance, the darker the image is going to get. And notice that here, the chess pieces that are closest to us are the brightest, and the ones furthest away are the darkest. And there is a picture of some superheroes coming at you, and the ones that are right in our face are going to be the brightest, and the other ones are going to be the dark. And there we are. This is a salute to you. You are the tech art fans. You are the tech artists of tomorrow. And we raise our cups to you because you're spending your time learning all about depth mapping so you can go about and produce better shadow looking images. All right. Okay, as a disclaimer again, I was not able to implement this properly inside of the vertex shader, so therefore I needed to rewrite the shader in order to actually export outside of the pixel shader. And the results are actually the same, but I needed to go about and make this disclaimer to go about ahead of time, is just so you wouldn't be surprised when I happen to show you something that just didn't quite make copacetic effect. All right, let's take a look at the contents inside of Shader Tool. Okay, this is where we left off last week when we were dealing with the projection mapping. Now, honestly, the projection mapping is going to go on and take off a whole new behavior in there because we're rendering a separate object. Now, this object that we render, we are just rendering the box, just in this case. And so therefore, if we wanted to rotate, let's see, the light box, so where's my object, my world space? Boom, 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 boom. Oh, wow, my world space is way down there. And so if we wanted to, we could move this around here. And then if we wanted to move our box around, we're rotating the box around. Okay, so what we're going to do now is that I'm going to come down to the scene, is I'm going to render a teapot. And this teapot is now going to be rendered in front of the scene. And therefore, what I'm going to do is I'm going to re-render the scene from the perspective of the light, and we're going to render the teapot as a depth map. That means we are not going to shade it exactly the way we would before. What we're going to do is we're going to shade it so that as parts of the teapot come closer to the light, the brighter it gets, and the further it gets away, that means the darker it's going to get. Okay, so we've got our teapot object into the scene here, and then and so notice what I had to do is I had to create my my world matrix on this. And my world matrix is basically I have my scale, where I can scale my let me see if I can push this over here, this control over here. I can scale my teapot, make it bigger or make it larger. Notice that as it gets bigger, it gets brighter and it gets wider. And likewise, I can rotate it as well. So notice that parts of the teapot, as they come close to the camera, are getting brighter, and as they get further away, they're getting darker. Okay, so I didn't worry about, did I Did I bother putting in the translations? No, I forgot to put in the translations, but for all intents and purposes, this is more than adequate. Oh, wait a second. I did put the teapot translations in here. It says right here, so we can move it into the X direction. Yeehaw! And then we can move it into the Y direction. All right, so we can now move our teapot exactly the way we expected it to. Okay, so what we got here is our teapot is in our world space, and then we have to put it inside of the projection space. But the projection space has to be not from the camera, it has to be from the light. And so, therefore, we have our basic let's see, we have our world space matrix going on here, but then we need to modify it by the view matrix. And then we're going to get our view matrix and our projection matrix from what we created last week. Now, I'm not going to go over all that again, and all this is gobbledygook going on here. But what we're going to do is we're going to get our world matrix for our teapot. We're going to multiply it by the view matrix from the light, and then we're going to multiply that by the projection matrix, and that becomes the new worldview projection matrix coming into our scene. And that really is all we needed, because what we're going to do is now render the entire scene from the view of our camera. So let's take a look at our map here. Now, everything pretty much stays exactly the same, and realistically, okay, come on, there you go. Let's get, oh yeah, there it goes. Got it bigger here. Okay, great. Now, other than coloring white, I did add a color black, and we did add a depth bias. But, you know, for this particular shader, we're not going to even deal with the C buffer per frame. Yeah, that's because it's not necessary. But we are going to deal with a C buffer per scene as far as our teapot is concerned, and that is going to be, I'm going to call that the C buffer per scene, and I'm going to call it my world light view projection matrix. All right, now for this we're not going to be dealing with any texture maps, but we are going, and we're not going to be dealing with any texture samples. We're going to be all using that next week when we put all that stuff together. But let's see, in the data structures, nope. We're not going to be using any of the data structures. We're just going to keep it simple. As far as the data structures are concerned, we've got our depth map input, and all we technically need is the object position. And then the output effectively is the object position. So nothing at all changes as far as that is concerned. Okay, let's take a look at the vertex shader. Now, I got to add as a reminder again, now in a normal rendering engine, the shadow depth maps are created in the vertex shader. In this case, they are not, because I couldn't figure out how to do it. So what I did was I just passed the information through my vertex shader. So here my depth map vertex shader, I got my input in, and then all I'm doing is transforming the object position into the world light view projection matrix. Okay, we're just multiplying that, and we're just putting that into the light view projection space of our light. And now we're going to deal with the pixel shader. Now the pixel shader is going to be ultimately very, very simple again. And there is all the stuff for the projection mapping. Now, this is a little embarrassing, gang. Check this out. This is all the pixel shader is. Now what I had to do was I rendered it, I passed it through, and then rendered the object as far as depth is concerned. But in doing so, check this out. I am taking the in position, and I'm taking its Z value as its Z value as its overall color, because I know that I'm going from Z, going out from very, very close to very far, and it puts it up. But what that does is it inverts the image. It means it makes it dark up close and then bright as when you go away far. So what I did was I just basically subtracted that from 1 in order to get my image to appear as bright white up close and then dark as it goes away. And that really all is as far as depth map is concerned. Now this is created as a separate pass from our projection. So whenever we do a projection matrix, we're going to render our scene, and then we're going to render the entire scene again from the perspective of the light. Now this is the reason why the shadow mapping takes such a long time, and this is the reason why shadows can get so expensive, because every single light that projects a shadow needs to render the entire scene as a pre-process and create its own individual depth map from it. You get me on that so far? And so if your scene is pretty complicated, and if you got 4 or 5 lights that are casting shadows, guess what? Every one of those lights has to compute its own scene depth map, and that all has to be done once every single frame for every single light. And so that's why things get so expensive, because if you have 5 lights, then it means you're calculating 5 shadow maps into the scene before you're actually rendering the scene according to that. Now we're going to continue this again next week, as we're going to take this depth map and we're going to use that information to integrate it with the projection map, and that's going to create our occlusion map. And then right after that, we're going to follow right up with how to create the actual shadow map, because the changes between the occlusion map and the shadow map are actually pretty small. And so we're going to combine those 2 steps, steps 3 and steps 4, into just one stage in order to create that effective shadow map. All right, so I'm going to go ahead and miniaturize this. Boom, boom, boom. Okay. And all right. Oops, you didn't. Oh yeah. Okay. Hopefully you don't want you wanted to see that. Hopefully you're taking a look at that. Okay, so let me see if I got that going here. All right, so let's move this along here. All right, so I invite you to come in again next week, where we're going to be going on and finishing up not only our shadow mapping, but we're going to be finishing up all our HLSL talks. And that will be, golly, on the 12th of November. Can you believe it already? So we're going to be doing part 3 of our shadow mapping, and we're going to be dealing with occlusion mapping, and we're going to deal with shadow mapping, and then wrapping the whole thing up. All right, folks, if you like what you see, go ahead and subscribe by pressing that little button in the lower right-hand corner. And if you want, my name is Chris Rhoda. Please check me out on Facebook and on LinkedIn, or check out TechArt.edu also, which is on Facebook and on LinkedIn. Okay, folks, that's all I wanted to show you today, and I look forward to meeting again with you next week when we wrap up all of this HLSL goodness and we wrap up our shadow mapping goodness when we're dealing with occlusion mapping and shadow mapping. All right, thank you very much. I'll see you folks again next week. Arrivederci.